17 from your homework, the wonderful problem number 17. That had x to the 5th, and you were all thinking, boy, Mrs. Payne, you are crazy for assigning this problem to us. So number 17 wanted you to find the limits as x approaches 2 of the function x to the 5th minus 32 over x minus 2. Thank you. So if you plug in 2, you get a 0 over 0. That's an indeterminate form. 2 in the numerator gives you 0, 2 in the denominator gives you 0. In order to evaluate this function algebraically, we have to be able to cancel out that denominator, which means that the numerator has to contain that exact factor so that it can cancel. So we do have to factor this problem like we did yesterday. Factoring is one way to evaluate limits algebraically to alter the form. So the goal is to get that whole quantity in the denominator to cancel so that you can plug in the value that the limit is approaching. Now, this year, we have talked about many different methods of factoring, putting little air quotes around that. We have factored using AC grouping. We have factored using difference of perfect squares. We factored using the SOAP formula. Those are all methods of true factoring. But there's still another way that we have factored this year. Peter? Long division, or what other type of division could we use? Begins with an S. What was that called? What type of division, Darby? Synthetic division. That's still factoring. And I did give you the warning that this chapter pulls everything together. So we are going to factor, but we're going to factor using synthetic division. Mrs. Everhart, the AP teacher who's next door, she was going over long division actually with her AP kids because one of the test questions probably going to contain long division. So they were reviewing long division. So like, I don't teach you this just because you really will be using these methods in calc next year. So they were reviewing long division yesterday and completing the square, which I was like, wow, we just did that too. So we're going to use synthetic division. Synthetic division does work because the denominator is linear. So we're going to take that 2 and it's a positive 2. Remember, that's x minus h or x minus whatever value is there. That's the factor, but the number you're dividing by is actually just the 2. That goes outside. And then inside, ooh, would be every coefficient from x to the 5th down to 32. Well, x to the 5th has a 1 in front. X to the 4th would be a 0. X cubed, 0. X squared, 0. X is a 0. And then you have the number 32. Every exponent must be represented. And then, Darby, do you remember how synthetic division works? Yes. So you're going to bring down the first term, and then you're going to multiply. So 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. 2 times 4 is 8. 2 times 8 is 16. And this is a negative 32. I missed that. And then I get a 32 and a 0. So the expression on the top is now x minus 2 factored out. That's what synthetic division is doing. You're pulling out a factor by using division. It's just a different way of factoring. Peter. Is there a formula where when both are there? Yes. And I like trying to factor it, and I only use guess and check. So there is a formula for like perfect cubes, perfect fifths, perfect sevenths. Yes, there is a formula. But synthetic division works pretty easily as well. And you can see that like this is 2 to the 1st. And then I have 4 and then 8 and 16. So kind of like 2 squared, 2 cubed, 2 to the 4th. So it is definitely a pattern there. So I have x minus 2 pulled out, and then the remainder is x to the 4th, 2x cubed, 8x squared, and then plus 16. That would be the remaining polynomial, your resulting polynomial. And that's over x minus 2. Yeah. Oh, yep, thanks. What did I miss? 2x. Oh, because that's an 8x. Thanks. So now the factor cancels, and that's the whole goal. You need that denominator to cancel out, because then you can substitute the 2 into your remaining expression, because it is no longer an undefined value once that factor is pulled out from the numerator and the denominator. So now you would have 2 to the 4th, and then 2 times 2 cubed, 4 times 2 squared, 8 times 2, and then plus 16. All of that is equal to 80. So the limit would be equal to 80. This limit is not reached. Anytime you cancel out the numerator denominator quantity, that creates the hole at that value it's canceling. So there's a hole in the graph when x is equal to 2 because it was undefined there. So you have a hole at that location. It gets really close to the value, but it's not reached. Questions? Yeah.
So is it only reached if you can plug it in?
Exactly, yeah. So any of the problems, which the first group of problems that you could just directly plug in, then it's always reached. So anytime you use direct substitution, your limit is reached. Good question. So if you can't directly plug it in, then the limit is never reached. Questions? So yesterday we were looking at ways to evaluate limits. Direct substitution is the easiest way because you can just plug a number in and you get out an answer because it is a function that is continuous. We then talked about factoring, which we just did, and most of the homework last night was either direct substitution or factoring. You factor so that you can get that quantity in the denominator to cancel, so that you then can plug the value that the limit is approaching in. The last problem we looked at yesterday was rationalizing, but we rationalized the numerator instead of the denominator so that we could get the x out of the denominator. So we needed that x to cancel. Whatever part's making it undefined is the term that we need to cancel out. And we did that by rationalizing. So another way to evaluate limits when you don't know what to do, which really should be the end all be all, the last resort, is to graph it using your technology. So I'd like you to graph this function in your calculator, the limit as x approaches 0. We're looking at the sine of x over x. Graph it in your calculator, make yourself a little sketch. And let's see if we can evaluate the limit. So anytime you're given limits of trig functions, you'll want to graph that in the calculator, unless you can like just plug it in and evaluate it. But here, if I plug in a 0, I cannot evaluate it. So if you have no way to solve it, break it down, change it algebraically, especially if a trig function is involved, plug it in your calculator and graph. And this graph looks like a little mound. Does anybody know what the max of that mound is? How high does that mound go, Peter? It is 1. Yeah, that mound goes up to 1. You can check that by going to the table of values. It should have a y-intercept at 0, 1. So that should be the peak of the mound. And I'm just going to make mine a little higher. I'll make that little mark 1. So it skims along. And then it kind of goes up, then it comes back down. So the limit as x approaches 0 from the left and the right would be the peak of the mound of that curve. And that is at 1. But remember, at the value, there really is still a hole in the graph. There's a hole in the center of the graph because that value is undefined. So even though the calculator doesn't appear to have a hole there, if you can't plug the number in, then that number doesn't exist. So there's a little hole at the top of that peak. So technology can be used. It's not like I'm saying don't use it, but it should be used as a last resort. If you can't do some algebraic process that we would have talked about this year, then plug it in your calculator and make a little sketch. But if that's what you're doing, then that's your work. So make sure you're providing that. So show me a little sketch. How did you get the limit? Questions? So there are two other concepts that we're going to talk about today. One is called a one-sided limit, and the other one we're going to look at something directly from calculus. A one-sided limit says a limit can fail to exist if it approaches different values from the left and the right of C, which is what we talked about yesterday. So if the limit, one side is going above and the other side is going below, and it has different values on the left and the right, and that limit doesn't exist. It says this type of behavior can be described more concisely by the concept of a one-sided limit. So a one-sided limit, notice the crazy notation here. This is saying X approaches C, and then there's a little minus sign as the exponent. So we're not saying negative C, the exponent is saying we're looking at C on the left side. So a number, an X value, has a left and it has a right. And if the C has a negative exponent, then it really means we're looking at the number only on the left side of that number. So on the left side of 2, on the left side of 3. The plus says we're looking at that number from the right side. So every X value has a left and a right. If I was X, I have a left side and a right side. Numbers have both sides. They have two sides to them. So we're going to graph this following function. You can plug this in your calculator as well. And I added like this Apple TV is so slow today. Holy cow. I even restarted it yesterday. I added the two one-sided limits that we're going to look at. So you're using the absolute value of 2x over x. I want you to graph that in your calculator. Make yourself a little sketch, and then we're going to add the one-sided limits so that we can kind of look at the graph from the left and the graph from the right. So remember how we plugged absolute value in yesterday. Go to math, over to number, absolute value. Make yourself a tiny little sketch. Remember what is actually happening at the value of 0 are open circles. Make sure you're graphing those open circles at the value of 0. So on the left side, the graph is down. And on the right side, the graph should be up, going the other direction. So we looked at a graph similar to this yesterday. But again, remember, at the value of 0, it can't exist. I can't plug a 0 in. So that value has those open circles. So Hannah, if you're on the left side of 0, so that's what this 0 with the minus means. We're looking at the left side of 0. What is the limit of the line that's on the left side of 0?
What is -2?
Yeah, it's -2. So here's the left side, and that line, that limit is going to go to the y value of -2. So the left side of 0 has a limit of -2. Hannah, if you're on the right side of 0, looking at that line that's on the right, moving from the right toward 0, that limit is 2. So I have a left-sided limit and a right-sided limit. Because they're different, the limit of 0, Hannah, if there's different than the limit at 0, we would say there is none or it does not exist. But you could be asked just to find a one-sided limit. So it could exist on the left side and it could exist on the right side. But if those numbers aren't the same, then the limit at 0, we'd say does not exist because it approaches two different numbers. Questions with that? So there's one more graph that we're going to look at. And it's a little piecewise graph. And then there are the limits, the right side and the left side of 1 that we're going to look at. But let's first graph this piecewise function. So the first function says 4 minus x when x is less than 1. So that equation is really negative x plus 4. That's what we're graphing. And then we're only going to graph that when x is less than 1. So let's focus on graphing that line first. That line starts up at positive 4, and it has a negative slope, down 1, right 1. We're up 1, left 1. So I'm not going to connect my points because we're only taking the piece of the line where x is less than 1. So I'm going to go where x is 1. And at the point where x is 1, it says x should be less than 1. So at that point, I'm going to place an open circle. Which side of the line would the x values be less than 1? So can I connect the points that are to the left because that's where it's less than 1, or the points to the right because that's where it's less than 1? Jenny, which side do you connect? To the left. So you're starting at 1, open circle, connecting to the left. And then erase the rest. And that's the piece of the line where x is less than 1. And again, it's an open circle because it says less than. The next equation says y equals negative x squared plus 4x. Now you could do two things here. You could plug in some x values, or you could plot it in your calculator as well and get the x and y values from the table of values in your calculator. But we need to graph that parabola. So if you want to plug it in your calculator, graph it in y equals, and then get some points from the table of values. But we need to graph a couple of points. And the points that we want are when x is bigger than 1. So those would be the values that I want to look at in my t-chart or my table of values. So get some values where x is bigger than 1. So plot a couple of points. And you might want to look at the value where it's equal to 1 so that you know where to start, because that's where your open circle goes. So at the value of 1, if I plugged a 1 in, I would get 3. So when x is 1, y is 3. It stays as an open circle because it says x is greater than 1. So actually both of these graphs are meeting at the point 1, 3. And then if I plugged in a 2, it would go up to 4. And when I plug in a 3, it comes back down to 3. And then Darby, did you plot a point at the x value of 4? What was that value? 4, 0. That would be our intercept. So this is a parabola. It goes up to the max and then curves down. So that would be my graph. So I have a line connected at the same place of the parabola. So evaluate the one-sided limit. The first one says we want to look at x from the right side of 1. So again, this is saying look at the right side. That means that's the parabola part. So as we're on the right side, Parker, when I get close to 1, what is the value of the function when we get close to 1? So the x is 1. What's the y value? 3. Yeah, the value of the function on the right is 3. Parker, if you're on the left side of 1, now we're at that line, and we're coming into the x value of 1. What's the value that that function's getting really close to? 3. So if they're both the same, Cole, what could you say the value of the limit when it approaches 1 is? Just 3. So if your limits are the same from the left and the right, then that limit would be 3. Cole, is that function reached? Is that limit reached? Correct. Why? Yeah, it's an open circle there. There's not a point. So it gets really close to that, but the limit is not reached. Questions? So if the one-sided limits are the same, then the whole function at that value has a limit. If the one-sided limits are different, then that limit does not exist. Any questions? So the last thing that we're going to look at today says a limit from calculus. And if you look at number 4, just look at that part right there. F of x plus h minus f of x all over h. Does anybody recognize that? Look a little familiar, maybe. We did this in chapter 1, way back at the beginning of the year. So chapter 1 would have been September, mid-September, after we did our prerequisite review. And this was called the difference quotient. And when we looked at it, I really did say that this is calculus. It was an intro to calc right away. So this form is called the difference quotient. In 2 weeks, we have 3 weeks remaining. So in 2 weeks, you will see how this difference quotient ties in graphically with functions, because we're going to kind of build on this difference quotient. Right now, it's asking us to find f of x equals the square root of x. That's our function. And we're supposed to find the limit as h approaches 0 of f of x plus h minus f of x all over h. The new part is this limit part. So we're going to now try and find the limit as h approaches 0. This part we have done, hasn't been for a while, but we have worked on that difference quotient. So let's review what it means. The first part says f of x plus h. The f in front means you have to go to the function and replace whatever's in parentheses into the function itself. So instead of saying the square root of x, this is saying the square root of x plus h. So that's f of x plus h. So you're taking whatever's in parentheses and going to the actual function, which is the square root of x. Then it says subtract f of x. Let's write that in a different color. So here is f of x plus h. Then we're subtracting f of x Well, f of x is the square root of x. So I'm subtracting the function. So again, you're using the function notation and replacing it with the actual function itself. But inside, the x is now x plus h because inside the function is x plus h. Then you're subtracting the function. Well, you have to replace that with its actual equation. What is the function represented by? It's the square root of x. In the denominator, it's just h. It doesn't have an f in front of it. So that means it just stays as h. Now, the only thing I'm going to add is the fact that we're supposed to find the limit as h approaches 0. So I have the limit as h approaches 0, the square root of x plus h minus the square root of x all over h. I cannot plug in 0 for h because then it would be undefined. So instead, we have to do something algebraically with this function to alter its appearance so that we, God bless you, can evaluate it. So what could we do with this algebraically to alter the appearance of the function? Peter? Unfortunately, no, because like that is contained underneath you, and that's a quantity with a plus sign. So we can't factor out an h. Like somehow, or factor out an x. Somehow our goal is we need this denominator to go away. Yeah, what's that called? What's it called when you multiply it by the plus instead of the minus? Jenny? The conjugate. We will use that conjugate fact a lot in math. So we're going to multiply by the conjugate so that we get rid of the square roots. That's the goal here. Can I get rid of those square roots in the numerator to help me get rid of that h in the denominator? So we're multiplying by the conjugate. When you multiply, remember the conjugate really uses the first terms and the last terms. The middle terms, the inner terms cancel. So the square root of x plus h times the square root of x plus h is just x plus h. And then my middle term, positive, negative, cancel. We're not even worried about those middle terms. The outer terms is a negative root x and a positive root x. Well, that becomes minus x. The denominator, we're going to keep in factored form. There's an h, and we're multiplying by the conjugate. I'm just going to keep it as the conjugate. Keep the h out with that quantity, root x plus h plus the square root of x. So notice in this problem, the x's are going to cancel. And then, because I have an h remaining and an h that's being multiplied by that quantity, those h's also cancel. And that's our end goal. Can we get that h in the denominator to cancel so that my denominator is no longer undefined? So what we have left, sorry, that's supposed to be an h that changed to an x out of habit, is a 1 in the numerator, because when terms cancel, when you're multiplying something on the top, dividing it out on the bottom, you get a 1. And then we have the square root of x plus h plus the square root of x. Darby. Yes, and you will see that with functions, you're going to have square roots in the denominator when it like pertains to functions. So if it was just a number, then we usually rationalize a number, but a function, you're going to have square roots in the denominator. So Darby, what function did you have when you plugged in that 0 for h? What are you left with? Yeah, so if you plug in a 0 for h, you end up with the square root of x plus the square root of x. And if you're adding one square root of x and another square root of x, you end up with 2. Questions? When you start calculus next year, this is what you will start with. You'll start with limits and you'll start with these problems. We're going to go through a ton over the next 3 weeks. We'll just really be working on problems spiraling from these. So let's try another one. Because some of you, I think your heads are spinning a little bit, like what the heck is she doing up there? Why don't we look at number 6? The hardest part, I think, is getting that setup step and understanding that you have to take the x plus h and go into your function, not the opposite way around. So we need to use the function x squared minus 2x and change the x in the function to be x plus h. So x squared is x plus h quantity squared. Minus 2x is negative 2 times x plus h. So again, this whole expression represents f of x plus h. And then it says subtract f of x. Well, whatever represents f of x, you have to subtract all of that. Well, f of x is x squared minus 2x. So we're subtracting that whole quantity, and make sure you're subtracting the entire quantity, not just the first term. So again, here's f of x plus h. I'm subtracting f of x, the equation represented by f of x. And then in the denominator is h by itself. In front, the end goal is to find the limit as h approaches 0. That's the new extra part that we didn't do the first chapter of the year. So Jack, what would you do to start simplifying this really big expression?
You could FOIL x plus h squared.
So if I have x plus h times x plus h, what would that FOIL to become, Jack?
X squared.
And then keep going, Jack. Awesome. And then all over h. Maybe it's coming back to you now. You might recognize this a little more. First one looked a little weird having that square root in it. This is a huge expression. With this huge expression, Joe, what happens? And then the 3 terms that are remaining, what do all 3 of those terms have in common, Joe? They all have an h in them. Remember, we need to get that h out of the denominator. It cannot be there because I can't plug a 0 in. So if you factor out that h, we're left with 2x plus h minus 2. All the terms remaining should have an h in common so that we can get rid of the h in the denominator. So now those h's cancel. We are left with 2x plus h minus 2. When you cancel the h out of the denominator, then you can use substitution, and that 0 goes in place of h. You're going to be left with an equation now, and that equation is 2x minus 2. I will tell you that that equation relates to a graph, and we'll look at that, as I said, in the next few weeks. We have 3 weeks left, so we'll get to kind of see graphically how this is kind of tying in. It really does mean something about the graph. So, fun Friday, Jenny.
Should we leave it as 2x minus 2?
Yep.
Well,
You can, you know what, you can leave it as 2x minus 2. So I'm just leave it like that. Good question. So your homework is definitely more algebraic than the last 2 days. You'll be rationalizing. You'll be doing some foiling, combining like terms, getting things to cancel. On Monday, we have no extra notes really to go over. I think I'll go over one of like the warm-up extra example problems. But Monday is just a time for you to kind of practice in class. No new concepts to cover on Monday. And then Tuesday, we have one other little addition to add to this. And then pretty much Wednesday, Thursday, Friday next week, we'll just be reviewing these limits. So have a fantastic weekend. Hopefully it doesn't rain.